Hello everyone and welcome back. Today we're going to talk about intervals, hypertrophy, and bundle branch block. Last time we talked about rate, rhythm, and axis. Today we're going to focus on interval, hypertrophy, and bundle branch block. And then next time we'll talk about R wave and T wave progression and ST and T wave changes. I forgot to add an R wave and T wave progression on the last one, but we'll talk about that one next time. So first let's take a look at the PR interval. The PR interval, as we reviewed previously, is from the start of the P wave to the onset of the R wave. And usually in adults, a normal value is less than 200 milliseconds. In younger children, their PR interval should be under 150 milliseconds. And that upper limit normally extends with time up to 200 milliseconds in late adolescence. Next, we're going to measure the QRS interval. Generally, it should be under 100 milliseconds for adults. For children under 8, it should be less than 80 milliseconds. So you're going to look at the QRS interval here to here and measure that interval in milliseconds. And then finally, the QT interval, you want to look at leads 2 and V5 to measure the QT interval. And what you're going to do is in milliseconds, you're going to measure from the beginning of the Q wave to the end of the T wave here. You're going to put QT in seconds, which is important, over the square root of the preceding R to R intervals. That would be a measurement from here to here, and that'll be R to R, and that'll be in seconds. So in this case, let's zoom in so we can get a good accurate representation. I'm going to count here that there are 1, 2, 3, 4, 5, 6, 7, 8 boxes approximately, and that would be 8 times 0.04 seconds, so that would be 320 milliseconds. In terms of the R to R interval here, I would have approximately 18.5 small boxes. So you do 18.5 times 0.04, and that equals 0.74. And so to get the QT interval corrected, you're going to do 320, but you're going to do 0.320 divided by the square root of 0.74, and that is equal to 0.372 seconds, or 372 milliseconds. For the QT interval, we're looking for anything less than or equal to 450 milliseconds, and that upper limit of normal actually extends a little bit more for adolescent females, in which case we say anything less than 460 milliseconds is normal. Next, we're going to evaluate for hypertrophy. And for hypertrophy, you're going to look specifically at V1 and V6. And for V1 and V6, you're going to look for large R waves in V6 or large S waves in V1 to suggest left ventricular hypertrophy. So large R waves in V6 are going to suggest left-sided forces because V6 is pointed out and to the left, versus negative forces in V1 are going to be more leftward as well. Tall forces in V1 suggest RVH, and then negative forces in V6 are going away from the left and therefore RVH. So for LVH, we'll use red. You're looking for a tall R wave and a deep S wave. And for RVH, if we use green, looking for a tall R wave in V1 and a deep S wave in V6. The other thing to look for would be a pure QR in V1. So that would be something like this. So no S wave in V1. So just a pure Q followed by an R. Next, we're going to look at atrial enlargement or hypertrophy. You're going to look at lead 2 in V1. So for right atrial enlargement, you're going to see if the P wave is bigger than 2.5 millimeters. Or in V1, if it's greater than one small box that can fit under the upward deflection in V1 before the downward deflection here. For left atrial enlargement, the width of it should be greater than 120 milliseconds, or greater than one small box in the downward deflection here. Next, we'll talk about the bundle branch block. In pediatric cardiology, we use the same patterns to evaluate for conduction delays from surgery or for hypertrophy, or both. Suffice to say that you are first looking for a prolonged QRS complex in V1 and V6. If the QRS complex is prolonged for age and there are late positive forces in V1, that would suggest late right-sided forces and hence a right bundle branch block. If you were to look at V1 and see late-sided forces, here being the QRS, and see how the late positive forces in the R versus in V6, if you saw something different where you would see late negative forces here, the late positive forces in V1 and late negative forces in V6 suggest a right bundle branch block because the energy is going rightward, and hence why it's positive in V1 and negative in V6. The alternative being if you are late negative forces in V1 and late positive forces in lead V6, that would imply a left bundle branch block morphology. Remember that the QRS complex has to be prolonged in order to qualify for right or left bundle branch block morphology. There is one exception to that, and that's the incomplete right bundle branch block. If the QRS is normal and you have an RSR prime in V1, so something that looks a little bit like this, here you have a little R, an S, and an R prime. But a normal, in this case, let's pretend this is normal, QRS complex. This would be an RSR prime morphology, and because it is not an abnormal QRS duration, it would be an incomplete right bundle branch block. And this can be associated with atrial septal defects and pulmonary hypertension. Here's an example of a right bundle branch block. Here you see the late positive forces in V1 and the late negative forces in V6. You see how right here it's negative, right here it's positive. Here's an example of a left bundle branch block. Here in V1 you have late negative forces, and here in V6 you have late positive forces. So you see here it's negative, you see here it's positive. I think that's all for today. We'll continue next time. Thanks so much.